Thank you. Actually, I'm not president-elect of NCTM. I am the current president for another 3 weeks, and then I get my life back. Bill Batters, the current president of NSTA, is a good friend. We've worked on projects together when he was at the Cleveland Municipal School District, and I was working at John Carroll. So good things come from Cleveland, I hope. So let me boot up my computer here. We're going to be two-fisted. I'm not used to working off of a screen there, so we're going to advance slides. By the way, up front, I will tell you that if you want my slides, you can email me. I will send you a PDF of them. I'm not sure there's much new there, but maybe you'll find something that you will find interesting and want to share. So I want to start by talking about what is STEM. Oftentimes, mathematics is the last letter of STEM and the forgotten quarter of STEM. And I want to talk about the importance of mathematics in particular in supporting the other areas of STEM. So in STEM, we talk about science literacy, we talk about technological literacy, we talk about engineering literacy, and then we talk about mathematical literacy. And I want to focus today on mathematics because so many people think that mathematics is just teaching kids how to do certain skills and then off they go to do them. And I would like to argue that mathematics can be just as innovative and support the other three letters of STEM in ways that perhaps sometimes we don't think about, either as classroom teachers, as students, and particularly as parents. And with the new Common Core standards, I know this morning Bill talked about the next generation science standards, so I'm going to take some equal time for the new Common Core math standards, which unfortunately have gotten a lot of pushback from people that don't understand what they're really about. It's amazing to me how misinformation can get out there. I have heard stories that the Common Core standards for mathematics were created by the devil, and if we teach them, our children will go to hell. I'm kind of wondering where that came from. I do think one of the more innovative parts of the standards of the Common Core standards for mathematics are the standards for mathematical practice. The mathematical content is pretty much when you decide to teach fractions, when you decide to teach Algebra 1, when you decide to teach what geometric concepts, it's the standards for mathematical practice that I think go hand in hand with the scientific and engineering practices. And they describe varieties of expertise that we want to build in children, in students of all ages, whether they're kindergarten and first graders or students in graduate school. We don't teach the standards for mathematical practice. We give students the opportunity to build those habits of mind. And here they are. So you'll notice that I've underlined some of the important words, and I'm hoping in a second I'm going to show you the science and engineering practices, and I'm hoping you're going to see an alignment between the two. With the standards for mathematical practice, we want students to make sense of problems and persevere in solving them. If you think about that for a moment, how do kids do science if they can't make sense of problems and persevere in solving them? We want kids to be able to reason abstractly and quantitatively. The whole world of statistics, I really believe that that is one of the strong content connections between science and mathematics. Kids have to be able to reason quantitatively. We want kids to construct viable arguments and critique the reasoning of others. Mathematics classrooms should be conversations and discussions among students. We want students to model with mathematics. We want them to use appropriate tools strategically. When do I need a calculator? How do I use a calculator? When do I use a computer? How do I use a computer? When do I use my head? And when do I use a pencil and paper? We want students to attend to precision. This is a little bit of a strange one. The first time I saw it, I thought, boy, we're trying to teach kids number sense and reasoning, and now they're saying kids need to be precise. They need to be precise in many ways. They need to be precise with language. They need to be precise with knowing not only what tools they're going to use to do mathematics, measurement being an important part of that, but also what is the appropriate tool or the appropriate measure that they're going to use. We want kids to look for and make use of structure, not only mathematical structure, but that mathematical structure is what leads to understanding what they're doing when they're doing science. And then also looking for and expressing regularity in repeated reasoning. And here are the scientific and engineering practices. Ask questions and define problems. Did you just hear that a few seconds ago? Develop and use models. Plan and carry out investigations. Analyze and interpret data. Use mathematics and computational thinking. I would argue that that's in all the other ones that we just talked about. Develop explanations and design solutions. Engage in arguments from evidence and obtain, evaluate, and communicate information. So what I did, just in looking at them, and I actually moved ahead just a little bit. Oh, thank you. I forgot that I'm supposed to be pushing this button up here. So he's keeping up with me from the back of the room. I actually tried to look at a one-to-one correspondence. Now, this is not exact. In fact, I would move things around a little bit. But this, to me, when I look at the mathematical practices and I look at the science and engineering practices, I'm starting to wonder if we shouldn't be teaching mathematics and science at the same time instead of as two separate courses, even as early as kindergarten. All right, so now I'm going to do this right. So I began to think about the missing link is really problem solving and teaching kids to be good problem solvers. I gave a presentation on the mathematics and in the Common Core at a coalition meeting in Washington, D.C., and the lady sitting next to me was from one of the engineering societies, and she was talking, and the more she was talking, I thought, she's talking about the kind of problem-solving strategies, the kind of problem-solving thinking that I'm trying to get even my elementary students to do when I'm in the classroom. That I want kids to have intellectual curiosity and not when they reach a point where they're not sure what to do, give up. I want them to think creatively about what they can do. I want them to have some objectivity, so if something is working correctly, they recognize that. When it's not working correctly, they can turn around and head in another direction. I want them to be open-minded. I want them to use prior knowledge. That's such an important thing, is this connection to what I know to help me with what I don't know. How do we help kids to use prior knowledge? So often in mathematics, when kids get to a new topic, they tend to forget everything they've learned previously. And one of the, I think one of the really strong characteristics of the Common Core standards for mathematics in the content end are the progressions that we hear about, so that there's a build, there's a connection between what kids are doing from one grade level to the next. And so I would argue that everything that's on this list, teaching kids specific problem-solving strategies, let me go ahead once, would not only help kids mathematically, but they would help them in science. And so I think if kids can organize their thinking, if they see patterns, if they can think about making a diagram, make a model, guess and check, not wild guess and check, educated guess and check. Sometimes acting a problem out, using a graph, that's looking at the statistical end of things, making an organized list. I had a 6th grade teacher who took one of our workshops one summer, and she came back the following summer and she said, my 6th graders don't know how to make an organized list. They have no concept of how to think about things in an organized way, so therefore they tend to approach things randomly. No wonder they get lost. That we want kids to solve a simpler problem. Sometimes tackling the complex problem first leads us nowhere. If I can take it apart and start with a simpler case or simpler problem. To write an equation, to identify a sub-goal, is that something kids do in science? Is figure out what do I have to do before I can actually get to where I want to be? To make generalizations, and once in a while to just change your point of view. So in the Common Core, I think there are three things that, there are three legs to the stool that we call rigor. And I think that these legs have very strong connections to how we get kids not only to think mathematically, but also to think scientifically. So procedural skills have always been there. In fact, there's a big thing going on the internet right now about teaching kids conceptual understanding. Do we teach them conceptual understanding before or after we teach them procedural skills? Common Core would argue that we're doing this all at the same time. But if kids don't understand what's going on procedurally, if they don't have that conceptual understanding of what it means, the third leg of the stool just has absolutely no meaning at all. They don't know how to apply those ideas. So I think as we're thinking about applications of mathematics in the science areas, that conceptual understanding is as important in science as it is in mathematics. I unfortunately, in my elementary school career, learned science from a textbook. We didn't have a science lab. This was up through 8th grade. When it was time for science, we pulled out the book, read from the book, and moved on. It wasn't until I got to high school and we actually got to mess around a little bit in a science lab that I actually started to understand what science was all about. And the fact that I understood math pretty well was very helpful. So I want to give you an example. Now, this isn't necessarily a science example, but I think it's an example of the kind of problem solving we want kids to do. So we're going to do a little bit of math right now. Suppose you shook hands with everyone in the class or in this room. How many handshakes would there be? So everybody exchanges handshakes exactly once. And kids have to figure out how many handshakes there will be. And it's very interesting. I've seen 3rd graders line up out on the playground at recess time, acting out, going through and shaking everybody's hand, figuring out how to get organized to do that. I've seen 5th graders draw diagrams. I've seen middle school kids make a table. And I've seen high school kids, Algebra 1 students, actually generalize and come up with a formula. Why I like this problem, and I'll show you some different ways to approach it, is that when I used to give this to my kids as their problem of the week, I taught only mathematics. I worked a lot with the science teacher, but my job was to teach mathematics. Kids would come up to me when they thought they had the answer, and they would say, Ms. Gojak, is this answer right? And I would look at them and say, you know, I'm not sure. And they would say, how could you give us a problem if you don't know the answer? Well, first of all, the answer changed depending on how many kids were in the classroom. If I had 25 kids in one class and 27 in another, they would get a different answer. But the kids were just absolutely floored that I did not know what the answer was. And I said to them, you know, when you're thinking about this, it's not the answer that's so important. It's the thinking that gets you to the answer. And I think that's also so true in science. It's the thinking that you use. I said, I can solve this problem. Now that I know how to do it, it's no longer a problem to me because I can solve it for any given number of kids. I just don't know the answer off the top of my head. And what's interesting about this problem, there's a numerical pattern that comes out of it. And that numerical pattern, which is triangular numbers, comes up in a lot of different problem situations. And the kids would say to me, they would recognize that pattern, and they didn't call it the triangular number pattern. They would say to me, that's the handshake pattern. So it's that using prior knowledge in, you know, when we talk about innovation, it's using prior knowledge to figure out what you want to do with new situations. So here's one example of how to solve the problem, and that would be to visualize it. A lot of kids are visual learners, and we're learning a lot about how we take advantage of that aptitude in kids so that they can visually see what's going on with the mathematics. So this is an example of what the kids did on the playground. They lined up and everybody shook hands with everybody else exactly one time once they got organized. And that's what that might look like visually. So how do I record that and talk about that? Making a table. And the table might include how many students. This is also starting with a simpler problem. What if I only had 2 students? How many handshakes would there be? What if there were 3 students? How many handshakes would there be? All the way to 10 students. And I can find some patterns as I look down the right-hand side of that table. I can see some patterns adding consecutive numbers. But the goal here is also for kids to generalize. So 5th graders usually get this far and they see the pattern, and I say to them, well, what if there were 1,000 people in the room? And they kind of go, you don't really expect me to go that far, do you? So now enters the whole notion of algebra, where I can start to generalize. I can graph the results and see what's happening, and see that that's not a linear progression. I'm not getting a line. So what's happening is as the number of people increase, it's not a constant increase in the number of handshakes. So in conclusion, this is what I say when I talk about these practices at math conferences. But as I was preparing this morning, I thought to myself, this isn't just the mathematical practices. I think you can put in the science practices, the engineering practices, and as I have opportunities to speak at STEM conferences, I learn more and more, and as I have an opportunity to study the next generation science standards, I'm learning more and more and understanding more and more about the important connections between science in particular and mathematics. And the technology and the engineering grows, and that's what gives us the problem-solving situations that we can provide for our students. So we don't teach practices. We have to design our instruction around tasks that give students the opportunity to use and develop the practices in learning and doing mathematics, science, using technology, engineering every day, not only in mathematics class, not only in science class, but in all aspects of their lives, including the potential for mathematical, scientific, and engineering thinking. So again, I thank you for having me. If you have not looked at the Common Core standards, I hope you've learned a little bit about them. I hope that you will go back to your schools and talk a little bit about the commonalities between the mathematical practices and the scientific and engineering practices. We had a lot of conversations about that when I was in the classroom. I taught on the east side of Cleveland. And we didn't always, that was before STEM became kind of the latest thing, and I worry a lot because I hope the latest thing doesn't go away. But I think STEM gives us an opportunity to really talk about how do we connect these different areas. And most importantly, how do we get kids excited about doing that and learning? Thank you very much.